Hello, I'm Emma Sumner and I'm a postdoctoral researcher at Goldsmiths University of London in the UK. I'm going to give you an overview of a study that my collaborators and I have recently published in Developmental Science. The title of the paper is Oculomotor Atypicalities in Developmental Coordination Disorder, and the research was funded by the Leverhulme Trust. Children with developmental coordination disorder, which we abbreviate to DCD, present with significant difficulties with acquiring motor skill. For children with DCD, motor problems are typically present early on in development and in the absence of any general intellectual or neurological impairment. Motor difficulties can have a significant impact on activities of daily living, and therefore it is really important that we develop an understanding of factors that may influence motor skill acquisition. In our study, we were interested in oculomotor function. When we complete motor tasks, we use our vision to guide our limb and body movements. The oculomotor system programs eye movements such as saccades and smooth pursuit eye movements, and as the foveal region of our eye is really quite small, it is important that the system operates effectively and executes eye movements quickly and accurately to ensure that we can process all the relevant visual information. So in this sense, our oculomotor system, or our vision, and our motor skills are interdependent. However, surprisingly little is known about the integrity of this system in children with DCD. To study the oculomotor system, we devised a short battery of tasks that examined fixation, saccades and smooth pursuit. We compared children with DCD that were aged 7 to 10 years to two typically developing comparison groups. The first matched to the DCD group by age, and the second matched to children with DCD by level of motor skill. So inevitably the second comparison group were younger. Eye movements were recorded using the iLink 1000 eye tracker. The camera was placed in the desktop mount underneath the computer monitor screen, and children used a forehead and chin rest as shown in the picture to keep their head stable. Prior to the eye tracking tasks, thorough background checks were taken to confirm group membership, and these included cognitive and more general fine and gross motor assessments. The oculomotor battery comprised 4 tasks that were administered in the order shown. The target was always a red circle, and the tasks were straightforward for children to complete. In the fixation task, they had to focus on the red circle, which was shown in the centre point of the screen, for 30 seconds, and they had to try not to look at any other part of the screen but the red circle. The smooth pursuit task had 2 trials, one slow and one fast, and they were told to keep their eyes on the target as it moved horizontally across the screen. Then for the final 2 tasks, the central red dot moved to the left or right, and the direction of this shift was always randomised. Now in the pro-saccade task, the children had to follow the red target when it moved, and they worked through 24 trials of this. But in the anti-saccade task, they had to look in the opposite direction when the red circle shifted either to the left or right. So they always focused on the centre point, but when it moved, their eyes quickly diverted to the mirror location. Together, these tasks allowed us to examine the execution of fundamental eye movements like fixation stability, smooth pursuit, and saccade performance. And the anti-saccade task also allowed us to consider top-down cognitive control, as this task required inhibition of saccades. What we found was that the fundamental eye movements were intact in children with DCD. In comparison to their peers, when in pursuit, children with DCD were able, at times, to track a slow and fast-moving target, so they were able to match their eye velocity to the target velocity. They were also proficient in executing saccades to a new target, doing so as quickly and accurately as their peers in the pro-saccade task, and suggesting that they did not have difficulty with oculomotor response preparation. However, we did find that children with DCD have difficulty suppressing saccades. This was evident in the fixation task, as they made more saccades away from the target than both control groups, and significantly more than their age-matched peers. Also in the smooth pursuit task, here we found that children with DCD made a high proportion of anticipatory saccades, where their eye was overshooting or over-anticipating the target at times. And finally, in the anti-saccade task, as shown, this latter task is particularly demanding and does require the cognitive control process of inhibition, and here children with DCD were similar to a younger control group, suggesting immaturity to some extent. Combined, these findings are encouraging as they suggest that the basic, fundamental eye movements are intact in DCD. However, the findings do suggest problems with executive control in this population. Problems with executive functions have been reported in children with DCD in neuropsychological assessments that focus on cognitive behaviour testing, but not oculomotor control. But taken together, the findings of this study and those neuropsychological assessment studies suggest that more attention should be paid to executive functions in DCD, and particularly in terms of thinking how executive problems may interfere with motor skill acquisition and making accurate judgments when navigating through the environment. We hope that future research will consider using oculomotor paradigms to better understand the neural underpinnings and sensory motor function in DCD. Thank you for listening to this snapshot of the study, and please do read the paper to find out more information. If you have any questions or comments, please do get in touch using the email addresses shown on the screen. Thank you.